This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning. When you're ready. All right. Can we start now? All right, thank you. So today's lecture is about stability. This is one of the most important concepts, properties of a system, and stability can be defined in different ways. So we will present two different definitions of stability, but you will see that both of these different stability properties will lead to the same test. So if you have a transfer function, you would be able to test stability, and you will see that the test is the same for both of these different stability properties. Right? So the first one is so-called BIBO stability, bounded input, bounded output stability. And the second one is just, we call it stability. It's basically telling you how the system behaves when you initialize it away from an equilibrium, whether the solutions will converge to the equilibrium or not. So this is the stability definition for systems without inputs. Right? So, and then we will present this Rauth-Hurwitz criterion, which is a very, very cool tool that you can use to check stability of a system without finding poles of a transfer function. So there will be an algebraic test, you know, that's an algebraic test that you can use to say whether the system is stable or not without actually computing the poles of the transfer function. All right. So we'll first motivate things a bit and then present two different stability properties. So BIBO stability, or bounded output, and just stability. And then we will spend some time talking about Rauth-Hurwitz criterion. And I will wrap up with conclusions. So if you think about stability, I mean, we already mentioned it in earlier lectures. When we talked about equilibria, there was stability, transience, robustness, right? So we mentioned the word stability. So what would stability mean? Well, it can mean different things. Actually, if you are interested in this topic, there would be books written exclusively on stability theory of dynamical systems, and you might find dozens of different definitions of stability, which would be all reasonable in different applications, right? So we will present only two such definitions, and we will present a test for these properties. So typically, you would require stability of, you know, any feedback control systems. I was asked the question, well, are there cases where unstable systems are important? There are such cases. You know, one good example might be, you know, continuously stirred tank reactor, where basically some variables just keep growing. You want to mix things, there is a chemical reaction, and you want to harvest as much product as possible. So things will grow, but this process will be stopped after a while, right? So in finite time, you know, maybe concentrations or the amount of product grows, right? And you are interested in harvesting this product. but typically you would stop this process after a while, right? In most systems, we will require stability. So an aircraft needs to have stable behavior. Cruise control in a car needs to have stable behavior. You can list hundreds of different examples where stability is necessary, right? So we will present two different definitions of stability. You may ask yourself, why do we need different definitions of stability? Because different applications may require different properties. So these different definitions of stability are attuned for different applications. So sometimes you might be interested in bounded input produces bounded output. Sometimes you might be interested in this other definition of stability I'll present. So as I said, there are books written exclusively on stability theory where you would find dozens of different definitions. Each of those different definitions might make sense in a particular application. Okay? So for both of these properties that we will present, we will give a test on how to test these things. So mathematically, algebraically, if you have a transfer function, you would be able to test whether the system is bivostable or not. So we want to have such a test, right? Later on, you will learn how to design controllers that achieve these stability properties in a closed loop. So we have a plant that you want to design a controller that achieves stability. We will learn how to do that via root locus, pole placement, and other design methods. In this lecture, we just want to look at analysis. If we are given a system, how can we test whether it's stable or not? All right, so we will consider, as I said, these two definitions. Bounded inputs imply bounded outputs, or bivostability. And then another definition is if we don't have inputs, would all trajectories in a neighborhood of an equilibrium converge to the equilibrium or not? Right? So we will talk about both of these. There are other definitions of stability, for instance, internal stability. We will talk about internal stability later on when we introduce sensitivity transfer functions. Lyapunov stability, if you decide to do advanced control, I do cover Lyapunov stability. And if you decide to do postdoc, like PhD, we offer subject of nonlinear systems. So you will be then almost exclusively talking about this Lyapunov stability. All right, so let's talk about bivostability. So what is it? Well, it says bounded inputs imply bounded outputs, but in order to say what's bounded, we need to somehow be able to measure signals. So we need to be able to measure how large input is and how large the output is, right? So we will use the so-called infinity norm. So the infinity norm here is if I'm given a signal, for instance a sinusoid, this norm of the signal, or U bar, would be the maximum over all time, positive time, of the amplitude norm of the signal. So in the sinusoidal case, this would correspond to the amplitude of the sinusoid. Right? So sinusoid would be bounded, and its bound would be equal to its amplitude, according to this definition. Right? And then, how about this Dirac function? Well, the description of the function is given here, and epsilon needs to tend to 0. Right? So 1 over epsilon would tend to infinity. So actually, Dirac function, strictly speaking, is not a bounded signal according to my definition. So what I'm interested in here, I'm interested in if I apply bounded inputs, would outputs be bounded as well? Now, why this might be interesting? Well, think about, let's first go to the system here. So what does this definition mean? Well, bounded input, would that always imply bounded output? For 0 initial conditions. In this case, I just assume 0 initial conditions. So why would this be important? Well, think about the pendulum. I love my stick. It's a teaching tool, I keep saying to my colleagues. It's a teaching tool. So this equilibrium here, you can sort of intuitively say, well, it will be stable, right? So if I sort of perturb it in any way, the behavior would converge back to this equilibrium. But what you can also say, well, if I apply, let's say, a bounded input, what would be a bounded input? Well, bounded input may be the force acting on this pendulum. So if I apply bounded force will the output, which is in this case the angle that this pendulum sort of makes with the vertical axis, right? This theta angle, would that be bounded? So if I apply bounded force, would the output be bounded? Well, in this case, yes, right? How about this equilibrium? Now this equilibrium, even if I have zero initial condition, meaning well you are at the equilibrium, you will stay at this equilibrium. So if you are very lucky and you position the pendulum exactly at the right point, and you don't apply any force, it will stay there. But if I push, this even with arbitrarily small force, it will go down, and it will stay down. So this intuitively would not correspond to bounded input implies bounded output, right? I mean, you have to be, also able to measure what you mean. How large? Sometimes we are talking about for small signals. Definition to be true for small signals, meaning if the amplitude here is not just bounded, but it's also sufficiently small, right? Then there would be another definition that we could use for that sort of behavior. So where would this be useful? Well, imagine you're flying in an aircraft and there's a gust of wind that has bounded force. Well, you don't want that gust of wind to take your aircraft off course. So instead of going to the States, you end up, in the Arctic, right? So bounded input, bounded output, you want to have behavior staying close to the original behavior you want, even if there are some disturbances. That's where this definition comes in handy. How can we analyze this? Well, it's very useful to think about convolution representation of the system. So, you may ask yourself, well, when the output would be bounded, but if I write output as the convolution, by the way, G is the impulse response, and this star here means convolution of impulse response with the input. We saw that this is one possible model for our system. Now, if I take the absolute value of the convolution, well, I can upper bound that by the integral of the absolute value of the impulse response times the absolute value of the input signal, right? So, but then this guy, if this guy is bounded, and it's bounded by u bar, I can take u bar outside the integral. So I take the u bar outside the integral, and what I'm left with is just the integral of the norm of impulse response. So note, if this integral here is bounded, then I would indeed have that whenever this u bar is bounded, y bar would be bounded, y would be bounded, right, for all time. So I would indeed have that bounded input implies bounded output. Yeah? So what is the test then? Well, the test is that this integral, which is the integral from 0 to infinity of the norm of impulse response, is bounded. Right? This integral is just a constant. It's just just a number, right? So if this is bounded, so what I mean by bounded, well, it's less than infinity, right? Then we are good. Well, what is the test? Well, for stability, well, this integral would be hard to compute in general. You can actually find a test that's much more elegant, and the test involves poles of the transfer function. So for transfer functions that are proper and rational, so meaning that more poles, an equal number of poles as the number of zeros in the transfer function. It's rational transfer function, and it's proper. Then Biot stability is equivalent to all poles of the transfer function being with strictly negative real parts, meaning that they are strictly in the left half plane of the complex plane. That's a test for stability, for bounded input stability. Control engineers have lame jokes, like any other engineering profession. So there is a joke, there's a plane, is, experiencing turbulence, right? And then the pilot, calls, could all poles please move in the left half plane of the plane to stop the turbulence, right? To stop this turbulence. I love telling lame jokes. That's my job. I tell my kids that's my job. Is that to tell lame jokes? So anyway, that's one. So it's easy to remember maybe you know, from this joke what the test is. So what would be the test? Well, you look at your transfer function, you find all poles. If all poles are with strictly negative real parts, you are good. You're bounded input, bounded output stable. Right. So most of the transfer function, you know, we would deal with in this subject would be rational and proper. So this test would apply. Right. All right, that's all good. Now I want to present a slightly different definition of stability, and this definition is assuming zero inputs, and I'm just looking at effects of initial conditions. So I'm saying if initial condition is not exactly at the equilibrium I'm interested in, would the solution converge to the equilibrium or diverge from the equilibrium or stay close to the equilibrium? So that leads to concepts of stability, instability, and marginal stability. So by the way, we will assume we don't have pole zero cancellations. Pole zero cancellations would, you know, lead to some tricky things. We will talk about that more later. So we will assume that there is not a single pole that is exactly the same as a zero in your transfer function. So there's no pole zero cancellations. So intuitively, what does this mean? Well, this picture from, you know, one of the earlier lectures really explains this stability property very well. So we always, when I talk about stability of a system, I always assume I linearize the system. So the equilibrium I'm interested in is the origin. But that means that the actual output is the same as some desired output, right, in my system. So look, if you think about these equilibria, this equilibrium, or that equilibrium, we can talk about their stability properties. So this guy, in the sense of that definition that I presented, is stable because if I put the ball here and then I just leave it to itself, no forces, no inputs acting, it will sort of oscillate if there is some friction and it will come back to the equilibrium at the bottom. So it's the same as the pendulum. So I initialize it with some initial condition, right, and I leave it by itself, and it will go back to the equilibrium. So that equilibrium would be stable in this sense. Now, if there is no friction, then this pendulum would keep oscillating. Similarly here, in this case, if there is no friction, this ball would keep oscillating, and then I would say that the system is marginally stable. Right? Marginally stable system is also, let's say, if you are interested in this equilibrium, but you initialize this ball here, and this is a flat surface, there is no forces acting, you know, on the system, so the ball would stay there. So it will stay close to the equilibrium you're interested in. It won't go far away, but it won't converge to it. So I would call that marginally stable behavior. And then obviously there is this, you know, behavior, equilibrium here. If you are right on top of the hill, you will stay there. That's the equilibrium. But if you initialize the system slightly off this equilibrium, the ball would roll off because there are no forces acting on it. And that's similar to the pendulum. If I initialize slightly off the equilibrium, right, just leave it and it goes away. So that's an example of an unstable system. In this case, we do not talk about inputs at all. Inputs are zero. Right? We're just talking about effects of initial conditions. So definitions are given here. So the system is stable if output converges for any initial condition, converges to the equilibrium of interest. Usually, when you linearize the system, in new coordinates, the equilibrium of interest is zero. So basically, we want to converge to zero in the new coordinates. As the system is unstable if output diverges, right? So you initialize it for some initial conditions, the output would diverge. By the way, if this happens for a single initial condition in a neighborhood, right, you would have instability. Definition requires that for all initial conditions you converge, and if there are some initial conditions for which you diverge, the system is unstable. Right? And then the system is marginally stable if your output stays bounded from all initial conditions and may converge to zero for some initial conditions, so depending on the initialization. So those examples I presented now would perhaps be special cases. There are special cases of each of these definitions. Right? Now, what are the tests to test these properties? Well, for stability, you would need, again, all poles of your transfer function to be with strictly negative real parts. Right? Now, I didn't ask, but in this case at least, do you see why poles need to have strictly negative real parts? Can someone tell me why this is the case? Why do I have stability if I have three? Yes?
Because the exponential, the would be x to the power minus.
That's right. So if you just think about partial fraction expansion, if you think about partial fraction expansion of a transfer function, right? You basically are developing everything as a sum of terms, where in denominators you have s minus alpha k, where alpha k are poles. Alpha k are poles. So if all poles have strictly negative real parts, taking inverse Laplace transform of the partial fraction expansion would give you a sum of terms where each term may have cosines and sines, but it will be multiplied by decaying exponential. Strictly negative real parts imply decaying exponentials. Right? So that's how you can see easily where this comes from. If you have at least one pole, with strictly positive real part, or a real part that's repeated and on the imaginary axis, you will have instability. And then if you have only poles either strictly negative with negative real parts, or some with zero real parts but non-repeated, then you have marginally stable system. So these are basically algebraic conditions for checking stability, marginal stability, or instability. Yeah? And think partial fraction expansion, and you can quickly find proofs for these things. You can quickly write proofs yourself. All right. What's a graphical interpretation? Well, the right half plane is a forbidden zone. So you don't want to have poles in the right half plane. So these crosses here represent poles of the transfer function, and you want to have all of them strictly in the negative part. In other words, strictly in the left half plane. The imaginary axis is also a forbidden zone if you want stability. If you want to have marginal stability, then you mustn't have repeated poles, right, on the imaginary axis. Otherwise, you will have instability. Does anyone know why I would have instability if I have repeated poles? Yes?
When you take the decimal class, you get like a T.
Yes. So you have polynomial terms that grow with T. That's exactly right. So that's right. That's the reason. So if you are off imaginary axis, right, you will have exponential either convergence or divergence. If you are on the imaginary axis, either you will stay constant if there is a single pole, but if there are multiple poles with multiplicity, right, then you will have polynomial divergence, right? So again, think partial fraction expansion. This comes from one of the earlier lectures that I told you, well, you need to know these things inside out, and this is now applied to stability. All right, so we are, about halfway through the lecture, and now we are ready to state a test called Raoult-Hurwitz test that you can use to check stability of a system, either bounded input, bounded output, or stability, without inputs, by not finding poles of the transfer function. This test has a really interesting history, actually, and I will tell you a few words about this test, but let's first explain mathematically what the problem is. So suppose you are given a transfer function. So you model your system via first principles, you found an equilibrium of interest, you linearized it, you found the transfer function, and now that's it. You got something like this. Right? You found your transfer function. Now, what we said was, well, the test is, for all the stability properties, if you look at the denominator, find zeros of this denominator, they are the poles. And then check whether all poles have strictly negative real parts. If we have some imaginary parts, we don't care about those. Strictly negative real parts. If that's the case, the system is stable. If that's not the case, the system is not stable. That's necessary and sufficient condition for stability. So how can we, look at that? Well, we need to look at the equation that looks like this, or we need to look at the equation. We can, if an is non-zero, we can divide everything by an, and then we end up with a monic polynomial. But then each of these coefficients here are basically ratios of these original coefficients and an, right? So if I want to convert everything to a monic polynomial, then I can do that. The solutions of the two polynomials won't change. So you can rewrite some monic polynomial like this as a product of s minus alpha 1 to s minus, so this should be n, not 1, this should be n, sorry, typo. So basically there will be n poles, and you can rewrite that polynomial this way. Now what the issue here is, often if I give you a polynomial of high enough order, let's say fifth order polynomial already, you would face problems of computing these zeros or poles by hand. So MATLAB can do that for you. It would use numerical methods, but you won't be able to find an analytic expression for poles as a function of coefficients in this polynomial. So what is really useful is to have a test that sort of says, well, poles are in left half plane, they are with strict negative real parts, but I don't know what they are, I don't care. I just want to test whether the system is stable or not, but I don't need to know the poles. So this test is called Rao-Hurwitz test, and we will learn how to do that now. Why this was really important? Well, in time before computers, it was much harder to calculate solutions of these equations. So people still wanted to be able to say whether the system is stable or not, but without computing the poles, which was hard. Right? So what we will present is useful in that case, but also the test we are presenting is useful when your transfer function depends on some coefficients that you can tune yourself. Imagine that you have a plant and then you want to design a controller. Now that controller might depend on some parameters that you can choose. Now when you find a transfer function using algebra block diagrams of a feedback connection of a plant and controller, you would obtain a transfer function here whose coefficients now depend on the tunable parameters that you can choose as a designer. So this test is also useful in those cases. Right? So you can then select regions of parameters that for which the system is stable. So this test can be used for design, as a design tool as well. Right? So multiple sort of motivations to do this. All right. So just some known facts. Well, if you have a quadratic polynomial, then if you want to set this equal to 0 and find its zeros, right? Then this is the formula, and you've seen this in high school, right? Now the problem is that it's not possible to do something like this in general. It's not possible to do that in general if you have polynomials of order strictly larger than 4. So you've probably never seen a formula because it doesn't exist. Now you can still do solutions numerically, but you cannot do solutions analytically as a function of coefficients of the polynomial. Right. So what would be a necessary condition? Well, it's interesting. There's a very simple necessary condition for arbitrary monic polynomials. Basically, if the system is stable, then the polynomial corresponding to the system would have to have all its coefficients strictly positive. If there is a single coefficient that's 0 or negative, the system cannot be stable. So, by the way, this is a sort of, you can reach negative conclusion, but you cannot reach positive conclusion. So you can use this test to quickly check whether the system is not stable. Right? But you cannot conclude whether the system is stable. Why? Because the system may have all coefficients strictly positive and still not be stable. Can anyone follow? So this test may hold, so all coefficients are strictly positive, but the system may either be stable or not stable. But if at least one of them is negative or 0, you know that the system is not stable. That's how you use this test. It's a necessary condition for stability. It's not a sufficient condition for stability. So sometimes, I might give you, an exam, a large transfer function, and I ask you to check stability. And then people try to do Hurwitz table, and the question is, what is the system stable? And one of the coefficients is 0 or negative. You should be able to immediately say it's not stable without doing anything else. Don't compute for me, because if you do that, you are showing lack of understanding, right? So don't do that, because it can trick you. Then people say, well, this was such a difficult exam. I spent half an hour computing the route Hurwitz table, but you didn't have to. You don't have to, right? If you use this test, you just apply it. Okay. Now, this test is also sufficient condition for first and second order polynomials. But first and second order polynomials are easy because you can immediately calculate what the zeros are. So you don't need this sort of test. It's trivial for first and second order polynomial. But it is true that this test is also sufficient condition. So how do you prove this? Well, note that an arbitrary monic polynomial with real coefficients, can be basically written as a product of terms like this. But since the test is also sufficient for first and second order polynomials, then if the system is stable, then A should be positive, B and C should be positive for any such term. When you multiply out these terms, you will get something that's positive for the full polynomial. That's the proof. Right? It's easy. So what's the test? How you use this? Well, if some of the coefficients are negative, or in your polynomial are negative or 0, you know that the system is not stable. But if all coefficients are positive, then we need to use Raud-Hurwitz criterion to check whether it's stable or not, because we don't know. If all coefficients are strictly positive, then we don't know. And we have to do more work. And that's where Raud-Hurwitz comes in. All right, so let's just look at some examples. Well, if you have an example like this, note what I have here is an example where coefficients in the polynomial depend on some constant. Imagine that this constant is part of your controller and that you can tune it. And then we are interested in a question for which values of k is the system stable. Because you would typically want to design a controller that stabilizes the pool. So maybe this sort of polynomial comes by applying algebra block diagrams to a feedback connection or a controller with a tunable parameter. Maybe controller is just k. Maybe controller just has gain k. In a feedback connection with a Planck transfer function, you will get a new transfer function whose denominator depends on k. And maybe this is how it depends on k. Well, then we can say, well, for this region of this interval of k's, you will have that this polynomial has all roots strictly negative real part. So now we have a parameter-dependent stability test. Here is a polynomial that has all coefficients strictly positive. This coefficient is 1, this coefficient is plus 1. This is coefficient plus 1, plus 1, plus 1. All coefficients are plus 1. But when you look at its zeros, when you put this equal to 0 and solve, you get this solution. Know that two solutions are exactly on the imaginary axis. So I would call this marginally stable. I wouldn't call this stable. Right? So what this tells you, I just found your polynomial where all the coefficients are strictly positive, but the system is not stable. You need to use this Raud-Hurwitz criterion to figure out, in this case, whether the system is stable or not. And Raud-Hurwitz will tell you, well, it's not. Yeah. All right, so we now come to the test. If you like crossword puzzles, this is the test for you. It's sort of, there's some logic behind, and I'll try to explain as well as I can, how to generate this sort of array of numbers. Formulas look complicated, but you have them in every book. It's an open book exam. You don't need to learn the formulas, but it's useful to learn how I'm going to explain it, how you form the array. And then we will present the test. Very interesting history. So, you know, I presented in one of the first lectures what's Flightwell Governor. It was an essential part of the steam engine. So, Flightwell Governor helped you control the speed of the shaft. If you wanted to maintain constant speed, you could use this measuring device. If you remember, you know, Flightwell Governor was basically a rotating sensor, so it was attached to the shaft, so it would rotate proportional to the speed of the shaft. But it had these masses that could freely move. So if you know, if you rotate faster because of centrifugal forces, these masses would sort of stretch more. And so if you rotate more, you know, you just relax your hands will just naturally go further away from your body due to centrifugal forces. Now imagine that you attach to those arms, you know, a leverage system that is connected to the valve that opens up sort of the steam, you know, from the turbine to the motor, more or less, right? So then you can close the loop and maintain the speed at a constant, pretty much constant value. So what did he just sort of designed it? Now there was a separate development in mathematics that basically Galois. By the way, look at the dates of birth and death. The guy was just 21 years old. He died in a duel, and he made a big mark on mathematics. So by the age of, I don't know, 21, I think, he made such a big mark. There's a part of mathematics called Galois theory. So a consequence of this theory, it says that you cannot find zeros of polynomials of higher order than 4 explicitly in terms of their coefficients. So that's a consequence of this general theory. So people knew that they could not find explicitly, you know, zeros of polynomials of high order. Now Maxwell, so this paper on governors by Maxwell, I mean, you probably heard Maxwell equations, you know, that's the same guy. So he basically wrote the first paper on control theory, and it was called on governors. So what he did, he basically modeled the system with its transverse function and showed that the poles need to be with strictly negative real parts for stability. But then he said, okay, I can calculate it for degrees 2, 3, 4. I cannot go beyond 5. I cannot do 5, 5th degree polynomials. So then there was actually an award. I think it's called Adams Prize. So Mathematical Society of Great Britain, England, that time, they basically would give problem to scientific community, and then Ralph basically won Adams Prize for solving this problem. Hertz solved it independently of Ralph. That's why it's called Ralph. You can see how technology and mathematics together led to really like a very precise question that was, you know, posed and important for engineering, right? To basically, you know, that led to development to mathematics. So there is interplay of technology and mathematics that goes hand in hand often. So I find this quite fascinating. But anyway, so here is the ugly beast. It looks like a Persian carpet. It's very busy, and you know, it looks like something that's very hard to master. But you are smart kids, you know. You will have no problem understanding this at all. So look, what we are dealing with here is only polynomials with strictly positive coefficients. I already told you that if some of the coefficients are 0 or negative, we know that it can't be stable. So this test is only for polynomials with strictly positive coefficients. So how do you form this table? So what you need to do first, you are given a transfer function that polynomial there is the denominator in the transfer function. And now you need to form this Round-Hertz table. This table would have exactly the number of rows that corresponds to the degree of your polynomial in the denominator of the transfer function. Note that I have here like Sn, Sn minus 1, S goes up to S0. So there are n plus 1 rows in this table. So how do you populate the first two rows? Look, the first coefficient here is just, you copy an from the polynomial and just write it down. You just take the highest coefficient in the polynomial. Then you skip one coefficient. No, this is n minus 2, an minus 2. So you skip one coefficient, and you keep going, skipping one coefficient at a time. When you run out of coefficients, if you still need something, you put 0. Right? When you run out of coefficients, just put 0 here. And then the second row is formed by starting from an minus 1. So you start from the second highest coefficient, write it down, and you keep skipping again one coefficient and going backwards. And you then populate the first two rows until you run out of coefficients. Right? If some coefficient, like if you need to use coefficient a minus 1 or a minus 2, just put 0 there if need be. Right? Now we need to talk about how to calculate these guys in the third row. And here is the general formula, but I would try to explain this formula a bit more. So what you need to always look at are two above rows. So note that coefficients in this row will be calculated using coefficients in the previous two rows. Right? Now how? What's the formula? Well, here is the sort of color coding that should help you understand what's going on. So I'm looking at this guy. I want to calculate what this guy should be. Well, I'm saying the formula is minus 1 over gamma 1, 1. Now gamma 1, 1, no, that's a coefficient right above the guy that I'm calculating. And then I have to form, well, this is a matrix. So this notation is basically the determinant of the matrix, right? Formed by these coefficients. So how do we form the matrix? Well, you use the, so I'm calculating this guy. So the red guys are basically the entries right above gamma 2, 1. And then the second, so that's basically the first column in this matrix. And the second column in the matrix is just these two guys. So that's the first coefficient in the third row. Now, how about gamma 2, 2? Now, you always keep the first column of this matrix with the same, so I'm now calculating this guy. So the first column and this guy are still the same as before. We always keep the first column, here to be from the first column of the array just above this row, right? And then these guys are now actually the next column. And that's actually the rule. If you look at the previous gamma 2, 1 formula, I was using always the first column and then the next column, right, compared to where gamma 2 sits. So basically when I'm calculating this guy, I always use first column and then the next column. If I calculate this guy, I would use first column and then the next column, etc. Right? So the formula is clean and you just calculate all of these guys. Now, you keep going until you start getting zeros, because if you keep going this way, eventually you will find that at some point both of these guys are 0, and then you will just start getting 0. So you stop there, you don't keep calculating. Once you run out of coefficients, that's it. How about the next? So you can actually, so basically the idea is exactly the same for all the following rows. You just apply the same idea but concentrating on 2 rows above the one that you are calculating, and it's the same formula. So that's basically what it is. So the formulas seem complicated, but actually once you get the hang of it, it's very quick. Again, you need to know determinants, you know, of a 2 by 2 matrix. So that's not really hard for you. By the way, do you know what the determinant of a 2 by 2 matrix is? I'm just assuming that you do. So it's these guys. So product this times that minus this times that. That's what determinant is. Yeah. All right. So here is the test. So Raoult-Hurwitz test says the polynomial with positive coefficients given here has all roots with strictly negative real parts if and only if. What does this mean? It's necessary and sufficient. This is it. You get the answer. If and only if all elements of the first column of the Routh array do not change their sign. So note that what you need to do is first you calculate this array, right? You keep going until you calculate this n plus 1th row. Then you stop. There's no more rows to calculate. And then you are looking at this first column here. Note that the first 2 entries in this column are positive because we assume that the polynomial has all positive coefficients. That was an assumption. The first 2 entries will be positive. But now if at some stage you get, 0 or negative, then we have a problem. Right? So if all coefficients in this first column are strictly positive, then you are good, you're stable. Now you may say, oh, but why did I have to calculate all these other coefficients? Well, to calculate this guy here, you need to do all these other calculations. Right? Just to get this column, right, you need to get these calculations. Now note what's the significance of this result. You do not need to solve a polynomial. You do not have to find its roots. You do not need to know what the poles are, but you can say whether the system is stable or not. That's one advantage. Another advantage is these coefficients here might all depend on controller parameters that you can tune. So you can then, by looking at the first column, where now all of these depend on some controller parameters, we can come up with conditions on controller parameters that guarantee stability. So this becomes then a design tool, right? So it's a very, very useful tool. And by the way, in an exam situation, there would be at least one question where you would have to use Raoult-Hurwitz criteria. It's inevitable. It's inevitable. Okay? Similar to linearization. I mean, you will have to do linearization, algebra of block diagrams. All of these would be elements in any exam. So here are some examples. Well, if you have just a first order polynomial, well, as I said, the first row, you just start from the first coefficient, and then you skip 1, but then the next one will be a minus 1. But a minus 1 is not there at all, right? The second row, we start from the second highest coefficient, and that's a0. Well, the next one, if we are skipping, that would be a minus 2, but that's 0, so we stop there, right? So that's the Raoult-Hurwitz first column. What is the condition? Well, all terms in this column should have the same sign. We shouldn't have sign changes. Well, do we have sign changes if both of these are positive? No, we don't. So that was the necessary and sufficient condition for first order polynomials for stability. How about the second order polynomials? Well, note here, the first row we start with a2, then we skip 1, then we write 0. So this is a2, a0. So we start with a2, skip 1, a0, that's the first row. The second row is we start with a1, then we skip 1, well, that is a minus 1. We just put 0 there. And then here, we just use the formula that I gave you, right? So this is the determinant, this thing here is the determinant. If you carry out all the calculations, you will see that the outcome is really a0. You plug everything into this formula. By the way, since I run out of some things here, I put 0, right? So, and I keep that 0 in the determinant. That's why I have here a2 times 0, that's this times that, minus a0, a1. That's the determinant I was telling you about, right? The outcome here is a0. So again, what is the test for stability? Well, A0, A1, and A2 should all be positive. That's the test. So we checked second order polynomials. Here is a more tricky one. Third order polynomials. You do the calculations. Everything is given to you, so you just go through these calculations for your own sake. I want to so there are several other examples. So I left these on purpose with all the calculations so that you can check how the formulas are applied. Okay. What I want to do is, just before we wrap up, first one is you can do things like this. So you are given a current, you are given a controller that depends on a parameter, and then you use algebra of block diagrams to find what the feedback connection transfer function is. You have a plant controller in feedback loop. You find the transfer function of the whole thing, and you would get that the denominator of this large transfer function is given by this. Now we can check for which values of k the system will be stable by forming a route array, and then applying the stability test. So here it is. When you do all the calculations, you will just find that if k is positive, you are good. Okay. There is one more trick that I want to give you before we wrap up. Note that the test here is saying, well, so route tells you what is the condition for all roots of polynomial to be strictly negative real parts. But if I asked you what is a condition, can you have a Rouse-Hurwitz criterion for a condition that all real parts are smaller than -10 or -1? What you can do is you can first introduce a new complex variable, which is basically shifted S. So basically, when S has real part smaller than -1, W would have real part smaller than 0. So you first do this transformation, and then, real part of W smaller than 0 means that real part of S is smaller than -1. So you form Rouse-Hurwitz array in W by replacing S by W -1 everywhere. You write that polynomial and then just apply the Rouse-Hurwitz test for W, which would be exactly the same as the test for S with real parts smaller than -1. I could have used here -10, -100, whatever. Right? So this is also a trick. There is, I think, in one exam, I think Michael Cantoni gave an exam where you had to basically find a condition for real parts to be between -1 and -5. So then what you can do is you can use Rouse-Hurwitz test, do similar thing like this, but then you want to have eigenvalues of one of the guys, transformed polynomials, to be unstable, to be on the right half plane with respect to some vertical y, maybe -10. So have a look at that one. I just leave you with these thoughts. If you have questions, you can talk to me. But this is, just another sort of trick that you can use to actually apply this test to other problems as well. All right. So just what we did today, we looked at different types of stability, bounded input, bounded output, and also stability with 0 inputs, just with respect to initial conditions. And we presented this algebraic test for stability, which was Rouse-Hurwitz test. Okay. So you do need to know how to use this quickly in an exam situation, all right? So please study this carefully. All right, thank you.
I was wondering about the changes in signs. I know that they have a meaning, but I don't know what it was. Roof array, if there's a change in sign, first...
You can count the number of poles with strictly positive real parts. If the changes of signs are from plus to minus and minus to plus, you can count how many poles you actually have in the right half place. So how many has stable points?
Oh, how many? So each
Yes.
time its sign changes by
Yes,
7 points.
yes.
Do you know the location of those holes? No. I just know that there's that many.